I'm going to talk about a joint work with Itai Cohen and Gal Maor. These are two of my PhD students, and it's a work that we are about to publish about tight bounds for the Zig-Zag product. It's going to be a non-technical talk, very introductory. What I'm aiming to do is to try to explain what are we trying to do, and also cover not only this work, but actually two other works that we had, but we'll see as we go. Okay. So let me remind everyone what are spectral expanders, because this exact product was aimed for the construction of spectral expanders. It's going to be a very short recall. So, right, so when you do graph theory, you're given a graph G and you work with it combinatorially, doing whatever combinatorially things you do. In spectral graph theory, you take a completely different approach. Instead of looking at the graph as vertices and edges and so forth, what we're actually doing is looking at the graph in a sense in the right basis. So what do I mean? For example, but that's the main example, you can look at the adjacency matrix of the graph. And if the graph is undirected, then that matrix is going to be symmetric, right? And we know, maybe you forgot, but we know from linear algebra that if you have a symmetric matrix, then it has a basis of orthonormal vectors, eigenvectors of Rn, right? So there are n eigenvectors, if n is the number of vertices of the graph. They are orthogonal to each other. You can normalize them. So they are orthonormal, and they form a basis for R to the n. And moreover, the corresponding eigenvalues are going to be real. They're always real because of the symmetry of Ag. So if you want equation, it looks like that, right? So you can decompose the matrix, the adjacency matrix, as this sum, where you have n summons, and each summon is just lambda I. This is the corresponding eigenvalue, the ith eigenvalue, times this projection matrix, psi I transpose. So psi is the eigenvector, and for any v transpose is just the projection operator to that vector. But if you like pictures instead, then you can imagine that instead of looking at this graph G as, and this is the Peterson graph, by the way, as looking at the vertices and the edges, you can encode it using kind of the right basis, not the vertex kind of standard basis, but the basis that takes into account also the edges of the graph, right? The structure of the graph itself, not just the vertices. So you have these, in this case, 10 eigenvectors. They are orthogonal to each other, and in each direction, the action of the graph is very simple. You just stretch by a factor of lambda I, where lambda I is the corresponding eigenvalue. Okay, and because the all eigenvalues are real, we took this set, or more precisely multi-set of eigenvalues, and called that the spectrum of G, and we also order it from the largest one being lambda 1 to the smallest one, lambda V or lambda n, if n is the number of vertices. Right, so in spectral graph theory in general, not just when you talk about expanders, what you do is you stop thinking about the graph, at least not exclusively as a graph, in the sense that you have the vertices and the edges and you do whatever you do in combinatorics, but rather you look at it in this basis of eigenvectors, and it sheds a lot of light about the graph. In fact, even the spectrum, regardless of the eigenvectors basis, shed a lot of light on the graph. Particular, the largest eigenvalue turns out to encode interesting information about the degrees of the graph. You can prove all kinds of slam about that, but the one thing I want to take from this is that a graph is d-regular, namely every vertex has degree d, if and only if lambda 1 is d. Okay? Throughout the talk, we are going to work only with regular graphs. So lambda 1 is always going to be the regularity degree, which is in this case d. Lambda 2 is essentially the most important quantity for theoretical computer science. We will also be care about the lambda n, but let's talk about it later. Lambda 2 essentially measures connectivity, right? So for example, you can show that lambda 1 equals lambda 2, regardless of whether lambda 1 is d, by the way, exactly when the graph is disconnected, right? So the gap between lambda 1 and lambda 2 vanishes exactly when the graph is disconnected, and in fact, you can make it quantitative. You can show, and that's Chigger inequality, that if the gap gets larger, as the gap gets larger and larger, as lambda 2 gets away from lambda 1, the graph becomes, in some combinatorially well-defined sense, more connected, okay? So in computer science, we really like lambda 2s, which are small. And as I hinted to, lambda n is also very important. And by itself, it kind of measures periodicity in the sense that you can show that actually a conclusion from a corollary of Perron-Frobenius. You can show that this eigenvalue is at most in absolute value. It's usually negative, but in absolute value, it's at most lambda 1. In our case, it's at least minus d, because the graph is d-regular, but you can show that it equals d precisely when the graph is bipartite. And bipartite really is about periodicity too, right? Good. Now, the actual parameter that we care about is the maximum between lambda 2 and lambda n in absolute value. So these two together, so the maximum between lambda 2 and lambda n in absolute value, this quantity, this parameter is called the spectral expansion of the graph. And I'm not going to go into details, but at the end of the day, you want this number to be small, okay? So, just to recap, we have that the gameplay is between minus d and d. Lambda 1 equals d for d regular graphs, and lambda n is at least minus d. And what we want is that the distance between these two, or actually more precisely, the distance between these two and the corners will be as large as possible. Okay, you want all the eigenvalues to kind of be close together in that sense. Now, why do you want that? Well, if you have a graph G for which lambda G is small, then you can show that great things happen, right? So the graph is, in a sense, a sparse approximation of the complete graph, and the complete graph is great. And sparse is great also, because the complete graph is great in many senses, but it's expensive. You have a lot of edges, so algorithms will run in, say, n squared if n is the number of vertices with respect to that parameter rather than respect to maybe n. So in general, you kind of want to sparsify the complete graph, or in general, like dense graphs, in order to gain in time or space or what have you. And when lambda G is small, that happens, and you also get and this kind of manifests itself in all kinds of theorems, like the expander Chernoff bound, and the expander Hitter property, and the expander mixing lemma, and random walks mix weakly kind of theorem. And keep saying expanders, and when I say expanders, I mean every graph for which lambda G is small. Far away from D, I'll be more precise in a second, but not that precise. Now you can ask, okay, what's the limit? Is there like a limit? I'm thinking of D regular graphs. I have some D in mind. How small can lambda G be? Well, it turns out that there is a number, and that number is precisely this magical number. What's going on? It's this magical number, which I can't seem to. It's this magical number, 2 square root of D minus 1. But more precisely, you can prove a more quantitatively kind of interesting results. But one thing you can say is that there are only finitely many graphs for which lambda g goes below this number by some constant. So for every constant epsilon, you can't really go below that value, unless for, besides for some, couple of graphs. So asymptotically, that's the bound. And interestingly, it's actually tight. I mean, there are graphs attaining this bound. So there are derivative graphs. There is a derivative graph G for which lambda G is at most to the square root of d minus 1. Okay. I'm not quantifying D here, but that's generally the spirit of things. And just to recap, expanders are graphs for which lambda G is going to be farther away from the edges, say from D, but you also need lambda n to be far from minus D. And the Alongo-Pana bound tells us that this is kind of the forbidden area. You can't have lambda G sitting in that area, at least asymptotically. And graphs that for which lambda G sits right on the border of this bound, or maybe slightly below, because asymptotically doesn't mean you can actually go below, are called Ramanujan graphs. And graphs, 2 square root of d minus 1 is great. It's really kind of optimal. But for many, not all, but for many applications, you will be perfectly fine with having a lambda G which is some, square root, some d to some alpha smaller than 1, like d to the 3/4 or something like that. Other applications might be more, sensitive to that, but in many applications you don't really mind. And actually, in some applications, not too few, even a bound of something like alpha D suffices, like even a 0.990, not just 0.1D. So all of these are called expanders, kind of in a slang kind of form. But Ramanujan graphs are, of course, the most interesting and important one because they're extreme and optimal. And for some applications, it's really crucial, at least to have the square root of D. The 2, I never saw, well, there is one example I know that the 2 is actually important, but the square root of D is more important than the 2 that, of course, multiplies it. Okay, so I hope that's clear, and maybe we should see a couple of examples. So if you look at the length 6 cycle graph, which appears here, then each spectrum is going, it has 2 and minus 2 as eigenvalues. It has 2 as an eigenvalue because that's lambda 1, that's a degree. And it also turns out to it has a 1 and minus 1 as eigenvalues with multiplicity to each. Okay. The Alongo-Pana bound is what the yellow things that you see here try to demonstrate, but in this case, all the eigenvalues are actually in the forbidden area, but these two. So, what's 2 square root d minus 1 with these two? It's just 2. The Peterson graph that we saw earlier, it turns out this is its spectrum. It has one eigenvalue 3 because the degree is 3, it's free regular. But then the remaining 9 eigenvalues are going to be 1 and minus 2 with multiplicities 5 and 4 respectively. Also here, actually, the Alongo-Pana bound tells you 2 square root of 3 minus 1, which is just 2 square root of 2 or square root of 8. And all the eigenvalues actually lies in between in the forbidden area, which is kind of funny. You need to go a little bit higher in terms of the number of vertices, or choose worse graph if you want to actually see the Alongo-Pana bound in action, not just asymptotically, but okay. And you can ask, what's, if I draw a random d-regular graph in some natural way, maybe the union of d perfect matchings, then what am I getting? Then it turns out, and that was a question, that was an open problem for a while. It was Alon's problem. It turns out, and it's highly non-trivial, that a typical d-regular graph in the distribution I mentioned is known to be nearly Ramanujan. And by nearly Ramanujan, I mean that it almost attained this 2 to the square root of d minus 1 bound. It may be off by a little of 1, where this little of 1 is vanishes as the number of vertices increases. And this is a result by Friedman, and there are other simplifications, yet still very complicated proofs for that. But okay. And in theoretical computer science, we care less about the typical behavior and more about constructions, because we need the constructions to do whatever we want to do, to construct codes, extractors, whatever. So how do you get explicit construction of expanders? I mean, again, sampling a random graph will give you a great, but not Ramanujan necessarily, graph. By the way, I should say that it's not known whether, like, whether like a constant fraction or with high probability over whatever distribution you draw from, as long as it's kind of natural, you get a Ramanujan graph. You do experiments and you can see that there is a constant fraction, not close to 1, but some constant fraction depending on distribution, which will give you Ramanujan. But it's not known whether, I mean, it's not, there is no proof for that. So the typical behavior of Ramanujan graphs is extremely interesting and open to my knowledge. But going back to construction, so how do we construct expanders? Usually what happens is that you start with some, suboptimal construction, and then people come up with smarter and smarter ideas, building on previous ideas, and then at some point, maybe you get optimal constructions, Ramanujans. But here the story is kind of backwards. So there are the two famous works of LPS, Lubatsky, Philip, and Sarnak, and Margulis, that used heavy machinery from number and group theory to construct Ramanujan graphs. Very explicit, what's called strongly explicit Ramanujan graphs. Granted, not for every degree. The degree has to be prime or prime plus 1 or prime power plus 1 and so forth. But these are extremely elegant, beautiful constructions, very simple to state, but extremely hard to analyze. I must admit, I'm not. I should know more about it. So you get Ramanujan graphs already from the get-going from 88. I was 6 years old. Yeah, I'll feel a bit old anyhow. Okay. So the problem with these constructions, so the one problem with the construction was that, but that's kind of for mathematical, not for applications for computer science, was that it only gave you a construction for every degree, not for every degree. It didn't give you a construction for every degree, only for those restricted degrees. And the question was, do you really need, I mean, Ramanujan graphs are really rigid, like really tight. So do you need this kind of group theoretic group structure and so forth? And therefore, maybe there are Ramanujan graphs only for these degrees, or so it's unclear. And again, so I don't know, I would have done experiments. I'm not sure but it was unclear, and definitely it was unclear whether you can actually, maybe there exists, but you cannot. But you need something to argue that, and group theoretic arguments and number theoretic arguments kind of require the structure that requires, in turn, the degree to be restricted. Okay. So the other problem of these constructions was that you need to know a lot about the underlying mathematics in order to kind of tweak the constructions. I mean, we use expanders, but we also use expanders by tweaking them a little bit to whatever applications or thing we need. It's not always like a black box usage of expanders. So it was difficult to do that in these constructions, even though very recently there was this breakthrough construction of locally testable codes based on those. So, I mean, but on the other hand, Lubotsky is one of the authors, so maybe the L was useful. So anyhow, people really wanted simpler constructions that are easier to kind of manipulate and work with, maybe add some features and so forth. And the idea was to optimize for simplicity, and essentially the simplest but very elegant, of course, mathematical field is combinatorics, right? It's like a street fighting essentially. So people ask whether can you construct expanders combinatorially, and you can't really do everything combinatorially because at the end of the day you're shooting for spectral expanders, and spectral expanders are linear algebraic by definition. So when I say combinatorics, I mean plus like elementary linear algebra arguments. And there were a couple of constructions, but the golden boy in this line of work is definitely the Zig-Zag product by Reingold, Vadan, and Wigderson. I'm going to talk about that in a second. But I should say that there are other combinatorial constructions, such as the one based on lifting. This is idea due to Bilu and linear. And we'll see another one related to de-randomized squaring. But you can construct, at this point, there are a couple of ways to construct expanders combinatorially. And the analysis is going to be very elementary, again, very smart, but very elementary. And these were used to construct so many things, epsilon bias sets and codes and of all types, like locally correctable codes. For you can do distance amplification with them. You can construct relaxed locally correctable codes with them. You can do a lot of things with these expanders, with these constructions. I mean, by playing with them sometimes, and sometimes just use them as is. The problem is that they don't give you Ramanujan graphs per se. So Zig-Zag gives you something like d to the 3/4. You can play with it a little bit. Lifting gives you something which is better. It's like maybe some polylog away off from Ramanujan. So you don't bother writing even the 2, you're way too off anyhow, but that's a better construction. It has some disadvantages also, but this is the regime of parameters that you live in these combinatorial constructions. We do know how to get nearly Ramanujan at this point with combinatorial constructions as well. But okay, I'm not going to elaborate on that. So there was number and group theory, there was combinatorics, and the third kind of branch, the fourth way of constructing expanders is the topic of this talk, even though I said that the Zig-Zag is also the topic of this talk and it sits in the combinatorial part, and that's based on analytic machinery. Now, when I say analytic machinery, I don't know what exactly you have in mind, but what I mean here really is the use of free probability. But when I say analytic, I mean that you're going to see, all of these kind of Cauchy transforms. You may see some integrals here and there. You're going to use Haro rotations. Things are going to be smoother and very non-discrete. Okay, usually, unlike the number and group theoretic or combinatorial constructions. Even though you can argue that linear algebra is also quite smooth, but anyhow. So for example, in the maybe if I said that, I should also say that in the combinatorics, the linear algebra is always like a finite dimensional thing, and when you do analytic machinery, when you do free probability, like real free probability, you usually work in Hilbert spaces. You need infinite dimensional kind of linear algebra, which makes the problem easier, even though it may look harder. So anyhow, this started with a sequence of works, a fantastic sequence of works by Marcus Willman and Srivastava. And they constructed essentially Ramanujan graphs of every degree, so that addresses the problem with the LPS and Margulies and the following constructions. The problem is that they are only able to get one-sided Ramanujan guarantees. So by one-sided, I mean you only bound lambda 2 from above, you don't bound lambda n from below. Or vice versa, you can bound lambda n from below, but not lambda from above. And if you play with it a little bit, and they did, you also can construct a bipartite Ramanujan graphs. So I'm not going to delve into the definition, but it's an amazing result. Okay. So maybe before continuing on, I should just say that the point of these works is to do more with the analytic machinery. I mean, MSS, so there is this field of free probability, and MSS, as I said, free probability is really an infinite phenomena. It's an infinite thing. You always work with infinite dimensional spaces, and if you think about graphs, it will correspond to infinite graphs. And you don't want that. You want to construct expanders that you can, save on the computer or what have you. So MSS, in order to do that, they kind of developed what they call finite free probability. It's a theory that is inspired by free probability, but it doesn't use it. Kind of identifies the things, the phenomena, the theorems that they want to have, the structures that they want to have, and they just kind of prove it from scratch for the finite case. I think that by now there are other approaches to that that actually do use probability more, rather than do everything in a different way from scratch. But I'm not really aware of all the details, so I will leave it as that. But the point that we are trying to exploit is what we are trying to do is to use this fantastic framework that they constructed and also free probability itself in order to not just construct expanders. I mean, that's done. I mean, well, it's not done because you want to avoid it's definitely an interesting question, fantastic question to construct Ramanujan graphs, not one-sided Ramanujan graphs using this machinery or in any way, but we want to use the analytic machinery for things beyond constructing expanders. Okay, so in particular, we are going to understand the Zig-Zag product that I'm going to talk about next, and other products that I'm going to talk afterwards, and other operations using analytic machinery. So to use analytic machinery, not just for the construction, but also for just understanding how really these operations, like combinatorial key operations, behave in a way that I'm quite confident it's kind of too hard to do combinatorially. Okay, so let's take a step back and try to remind ourselves what is the Zig-Zag product before we go into the analytic machinery. So the Zig-Zag product was defined by this seminal paper by Reingold, Vadan, and Wigderson, three of the fathers of pseudo-randomness, some 20-something years ago at this point. And let me remind you what that is. So the Zig-Zag product is a product of graphs. You take two graphs, you produce one graph, and there is, in this product, you have the large graph G and the small graph H. You should think of G as like the ambient graph. Usually in applications, it's going to be a graph that was given to you from the sky. You don't have much control over it. Maybe you know something about it, but you don't control the graph itself. You can choose it. H is usually you can choose it to your liking. And so the focus is actually on H, not on G, on the small graph, because that's the graph that you want to figure out, which graph should I take. Okay, but more concretely, G is going to be a graph on n vertices, and you should think of n as very large, which is D regular, and you should think of D as maybe a large constant, or maybe some log n or polylog n. And H is going to be a graph on D vertices, which is exactly the regularity of the graph G, and it's going to be C regular, where you should think of C as a small constant. Okay. So before telling you what's the actual construction of the graph, the first thing you need to do, like the mental thing, is to take a copy of H and put it on every vertex of G. And by that I mean you place the copy of H, like the vertices around every vertex, but you also identify every vertex of H with an edge leaving that vertex. So that's what we did here, right? So this vertex is identified with that edge and so forth. Okay. So far I didn't tell you, that's not the graph. I mean, it's not a graph, it's just like two graphs painted on top of one another. So the way you actually construct a graph is as follows. So let me tell you, who are the neighbors of this vertex. So the vertex of this vertex, any vertex, are obtained by doing a zigzag walk. And by that I mean you get a neighbor for every yellow, blue, yellow edge that you can go for. So for example, this vertex is a neighbor of that vertex because you have this path. Okay? In general, you're going to have C choices for the first yellow step, which is called the zig step. And then upon, choosing one, you're going to go through the unique blue edge, like G edge, that is available to you. So there are no choices there. And then you again have C choices for how to continue. So altogether that's C squared choices, and therefore this graph is C squared regular, right? And note also that it is undirected, because if you have that's why you add the second step. If you add the zig, blue zag, then you can do the zag as a zig and go back. Okay, so this graph is on ND vertices. So I should have started by saying, of course, that the vertices are of this graph are the vertices of H, union over all copies of H that you have. So you have ND vertices, and the graph is C squared regular. Okay. Right, so this just summarize this thing that we just said. If G is on n vertices, it has degree D, and it has a lambda, which is I'm kind of switching here from lambda to normalized lambda. You see, we have two graphs, and they have different degrees, D's and C's, and it makes sense. It's worth our while, definitely, to normalize lambdas by the degree so that the numbers will be between 0 and 1. So I'm defining omega to be lambda divided by the degree here. Okay, and therefore this omega g, which is just lambda g divided by d, is whatever value you have. And for h also, this is a serial graph on d vertices with some omega, which is just lambda h divided by c. And the question is, what can you say about omega of the zigzag product? Right? We know that it's a graph on any vertices. You know that it's c squared regular, but what can you say about omega? Maybe I should emphasize that before. I mean, the graph is c squared regular. Its degree is completely independent of the degree of the large graph. And that's the feature of the zigzag product. It's a degree reduction procedure, in a sense. But you do want to maintain something about omega because you can easily do degree reductions by just doing whatever you want and destroying omega. So the point is that you want to do degree reduction, but to maintain a small omega. So the question is, how large can omega of the zigzag product be? And the main theorem of Reingold, Vadan, and Wigderson, who introduced this product, is that this is essentially bounded by the sum of the different omegas. So that bound is both incorrect and not what appearing in the paper. So you need actually, I mean, you can actually, it's actually not correct as written, but don't worry about that too much. If you add omega h squared, you're happy, and that's fine. But also, you can prove stronger bounds, but not sufficiently stronger so that it will be worth a while to look at them at this point. Okay, so you can think of that. That's as a first approximation. That's the bound you should have in mind. Okay. Now that's a bound, and that bound is used every time that you essentially apply the zigzag product. But is it like a bound or the right behavior? Right. I mean, in a world in which you can improve this bound significantly, you will have many applications. So the question is, fixing h, after you fix h, and again, h is the thing that you try to understand. You're trying to understand the operation of zigzagging with h. G is, it's not your control. It's like the input for the problem. And you have a problem for every h. So if you fix h, what can we say about omega of the zigzag product with h? What's the real behavior? And by real behavior, I mean not a bound, real behavior. But when you say that, it's still you have several branches that you can think of. You can think of the typical behavior, so that's analog to a random irregular graph, how close it is to Ramanujan and so forth. You can think about the best case scenario, which is what we are going to do. That's how good zigzags are, and you can think about worst case scenarios. So the RVW bound, for example, is an instance of that, because it tells you it can never be that worse than omega g plus omega h, plus the little I that I told you, it's omega h squared. So the nice thing, if you do complexity theory or coding theory, and you don't understand what you need to pull all the time, and the nice thing about spectral graph theory is that you can actually run experiments and see what happens. You can just use Julia or something, and just sample, say, a graph, or choose a graph and see what the omegas are. So let's do that. I mean, we did that. And when you do that, by the way, you immediately are in the typical setting regime, because you can't go over all possible graphs of size, any significant size. So the whole discussion now is going to be the typical case for this slide. So we took, here I'm going to take two graphs, the length 6 cycle and the Peterson graph. And what do we know? So the Alonbo-Pana bound gives us bound on how small omega, how small omega can be or cannot be for every graph which is obtained as a zigzag with h. Right, so it's only based on the degree. So the zigzagging with h will give you a degree 4, 2 squared graphs. And the Alonbo-Pana bound tells you, right, it tells you 2 square root of 4 minus 1, that's lambda. So 2 square root of 3, and omega is obtained by normalizing by 4, so that's the number that you get, right? So you can't go below 0.6, 0.86 when you zigzag with h, asymptotically. For the Peterson graph, it's an other number. It's 0.63 for the same reason. It's 2 square root of 9 minus 1 divided by 9. Now, on the upper bound side, the RVW is actually completely meaningless for zigzagging with h, because h has eigenvalue which is -2, so omega is 1, right? Because lambda g is going to be 2, and therefore omega is 1. And the bound that I gave you, and also actually the better bound gives you no information, namely a bound of 1, something which is anyhow between 0 and 1, on zigzagging with h. And if you look at experiments, you are going to get this 0.96 number with fluctuation after some point. For the Peterson graph, it's the same. If you use the better bound from RVW, you get this number. So you are guaranteed that you are not going to, omega is not going to be worse than, namely higher than 0.85. Alonbo-Pana gives you this, as I said, 0.63, and the real world actually gives you 0.79. So we started this project, and actually the previous projects also, by being completely powerless. We get these numbers and we have no way of explaining them or understanding them. I mean, what we aim for is a kind of a recipe that will take the graph h and will produce these numbers. And that's essentially what we have as our main theorem. In particular, in these examples, by the way, the 0.96 turns out to be the beginning of 1 plus square root of 3 over square root of 8. You will see why in a second, a couple of minutes. And for the Peterson graph, the expression is, we know it now, but it's not. It's okay. Let me just show you. It's this thing. So it's kind of a. When you look at it, you see that someone solved a cubic equation, I think, but it's definitely it was definitely fun to actually get this expression, compute it, and get the number that we always saw. It's hard to guess it. Okay, so what's the main theorem? So now with this introductory part, I think we're ready for the main theorem. And again, we don't know anything about the typical case. I mean, we know what happens because we can just see it on the computer, but we don't know how to prove that. Definitely because it's even that's probably a harder problem than the Ramanujan's problem. Namely, can you understand the typical behavior of Ramanujan graphs? So the techniques are not there yet. So what do we know? We know things about the best case scenario. Okay, so what's the main theorem? Well, we know. So for every, there is a little asterisk. Don't worry about that. So for every vertex transitive graph H, so it's the same H as before. It's going to be C regular and on the vertices. And for every degree D regular graph G, you need the regularity of G to be the size of H. We have a lower bound, hence best case, on omega of the zigzag of G and H. And that lower bound is obtained as the minimum of this function. So there is this function z sub h of x. So you have the 6 over c squared, then you have a square root, then you have this expression where little h of x is the characteristic polynomial of h squared. So note in particular that the entire spectrum of h, or more precisely h squared, is incorporated into the bound, rather than the Rosenman-Vadan bound, than the RVW bound, which only uses the omegas. Right, so I think it's kind of a general thing. I mean, at the end of the day, you want a bound on omegas, so it makes complete sense to bound the omega of the composition with the omegas that you started with. You do it all the time, not just in graph theory. For example, when you concatenate codes, you use the distance and rate of both codes in order to analyze the distance and rate of the resulted codes. And when you do correct LCCs and so forth, you always do that. But here we're actually using more about H in order to understand this parameter omega that we care about the zigzag product. And I think that's, I mean, since we are doing so many compositions in theory, then because it's sort of modular and you understand things like that, then it's definitely better to try and incorporate more information to the composition, right? So that's what's happening here in terms of the spectrum. So the entire spectrum of H is incorporated to the bound, and okay. And the minimum, by the way, is taken over all from C squared, the degree of the resultant graph, onwards, infinity. We'll see examples. You might kind of say, well, where is omega G? Like, I mean, the bound is with respect only to omega H, not omega G. Well, it's not really important because when you, so for example, looking at RVW, when you use the zigzag product, usually G is extremely large compared to H, and its omega is much smaller because it's a large graph. It has a higher degree, like the size of H, so it's easier for it to have omega G, which is small. So typically what you see is that this is negligible, sometimes equal, but in many cases negligible to that anyhow. So the focus is on how much omega H kind of destroys omega G to begin with. Or how much H destroys omega G to begin with. So here, instead of paying plus omega H, we pay whatever this theorem tells us we should pay. And you might think, okay, that's a lower bound, but that's a lower bound. I mean, how tight is it? Well, in a sense, it's tight. So let me be more concrete here. So it's one-sided tight in a very strong sense. So what do I mean? So for any graph H, so that's in completing the theorem. For any graph H and for any n, any number that you want, there is going to be a graph G, a large graph of size n, so that's n size, that meets this bound, but in the one-sided meaning, namely omega 2 of the zigzag is going to be at most the bound that we have here, up to this little of 1, which you don't care about. So the only issue is the omega 2, right? That's the only thing that stops me from saying the bound is completely tight. It's one-sided tight. And if you think about it, this part of the theorem is really kind of an analog to the Alon-Bopana bound. Alon-Bopana bound holds for the irregular graphs. Here we are working with zigzagging with H graphs, right? Graphs that are obtained by zigzagging with H. And this part corresponds to Ramanujan, the existence of Ramanujan graphs, namely graphs that meet the Alon-Bopana bound. And that's what you have here. So the tightness uses analytic techniques that even in the case of Ramanujan are only one-sided, and therefore we also inherit this disadvantage. But it's a very interesting problem to keep thinking of. Okay, and maybe a little remark about the H squared opinion here. I mean, you would imagine maybe the entire spectrum of H should kind of, definitely because of the tightness, should be employed. But I don't know, if you think about it, you're going to do two-step from H in order to, define the edges of the zigzag product. So it may make sense that you only need H squared rather than H in order to get the bound. What a bit confuses me all the time is that you also have this G step. So, but it is what it is. That because of the tightness, I'm not allowed to complain here. H squared is enough. Okay, so maybe let's do an example, 2 examples, starting with the C6, the length 6 cycle. So if you recall, this graph has this spectrum. So h of x, which is the spectrum of h squared, is given by this polynomial, because you have 2 with multiplicity 2 and 1 with multiplicity 4. And if you do a little bit of calculations, you get that this is Z6. Okay, it's an easy function to work with. I mean, you want to minimize it from C squared onwards. C is 2 here, so from 4 onwards. And that's the picture depicting this graph. So you can see that from 4 onwards, there is this minimum here. It always looks like that. And that minimum is exactly what I referred to before. Okay, so it's really easy. I mean, it's really easy to do that. For every graph H, that's a very easy graph, but 6 vertices. But for every graph H, you get this polynomial, you plug it in here, and you minimize, and it's essentially a rational function, because when you minimize, you don't really care about the square root. Don't worry about the square root being negative. It's not an issue there. It's negative here. Of course, it goes complex, but not where you want to minimize anyhow, not from here. So it's just a minimization of a rational function, and then you plug it into this square root of this rational function, you get an answer. I can't imagine a combinatorial way of doing that, of understanding how low can omega with zigzagging with H can be. And okay, that's what the theorem tells you. For the Peterson graph, you get, if you recall, this is the spectrum. And so you can compute H. I'm not going to bother do that. It's actually simple here because you have only 3 distinct roots for H. You plug it into the Peterson, you get this picture now, and the minimum from 3 squared, which is 9 onwards, is evaluating the function there. It gives you this scary expression. But that was hidden all the time. I mean, this thing is a property of the Peterson graph, and by extension, this number. Okay. Okay, so as I said, I'm not going to say anything about the proofs. I will say that the first part, this part, is based on analytic combinatorics. I rarely, or actually never saw a use of that in Fury. I understood that there are applications in algorithms, but I'm not aware of like applications in Fury, like in complexity, for example, or Fury, which is outside of algorithms, cryptography, coding theory, and so forth. So analytic combinatorics essentially tells you, if you have a class or a combinatorial class that you care about, maybe you count trees, maybe you count cycles in a graph, what have you, then you should look at its generating function. Usually you think of it formally. The generating function is just a formal way of presenting all the information for every different size. But you should think of it as a meromorphic function over the complex plane. Usually it's going to be meromorphic. And it turns out that the singularities of these functions are going to determine the asymptotics of the coefficients, the things that you care about. And analytic combinatorics is a way of doing that. So for example, tools that we use tells you that if you have this generating function, and if it satisfies a certain functional equation, then condition on this functional equation being nice, you can, by exploring this functional equation, understand where are the singularities of your power series, your generating function. These are extremely beautiful things that they use a kind of complex analysis, not just the basics of complex analysis to do that. It's really nice to play with and work with. And as an advertisement, I will tell you that Itai Cohen, my student, is planning on giving and he's also a co-author here, is planning on giving a course on analytical combinatorics in the next semester, the fourth semester of next year, 25. So you should come. And the second part is, so the tightness part of so if the first part was the Alonbo-Panna bound for zigzagging, where the second part is the existence of Ramanujan graphs for zigzagging. When that's based on free probability and finite free probability actually theory, I can't say much about that. I just say that in probability what you do is you study random variables which are commutative. And in free probability is kind of an abstract framework for studying in particular, but not only, non-commutative random variables. So maybe your random variables are matrices. Maybe you have two matrices and they are non-commutative. They don't have shared eigenvectors. And you want to understand what happens, say, to the eigenvalues of the sum of the matrices. That's generally impossible because you need the eigenvector structure. But it turns out that if the two matrices are free from each other, in a sense, then there is a way of doing that, and there is a precise description of how to do that based on all sorts of transforms like the Cauchy transform and the R transforms and so forth. Extremely beautiful theory, both free probability, which is the largest, and finite free probability, which is what MSS gave us. And I'm going to give a course about that in the coming semester in like 3 weeks. That's kind of part of the reason I'm giving this talk, to advertise that. And Gal, my PhD student, which is also a co-author on this work, is going to TA that. Okay, so we're going to have an hour in between to rest, but other than that, it's going to be fun. Resting is also fun. Okay, but that's that. So in the same paper, we also prove bounds, also prove an analog result for the replacement product. So I don't want to get into the definition of the replacement product. I would just say that it's actually a more fundamental product than the Zig-Zag one. It's folklore. I don't even know who invented it. I couldn't find any citations online. It's like, of course, you have the replacement product. Now, the replacement product is not going to yield you good expanders because it's not meant to do that. It's meant to do other things. But you can analyze how well can a graph which is obtained using by applying the replacement product of G and H. It's the same. You have a G and an H and so forth. How small omega can be. And here it turns out to be kind of much more difficult to get the equation. So if Z sub H was the equation that kind of captures zigzagging, then with H, then RH is the equation or the kind of captures the replacement product with H. And it's actually better, I'm not going to go into the details, of course, but it's kind of better to use the Cauchy transform rather than the characteristic polynomial. So the Cauchy transform is just this expression here. And you can actually also rewrite the original equation for the zigzag using the Cauchy transforms. It's slightly cleaner like that. Okay. And actually, in a previous work, we studied a third operator, which is called the de-randomized squaring. So the de-randomized squaring is a sibling of the zigzag product. It was introduced quite recently after that, by Rosenman and Vadan. And the reason that Rosenman and Vadan introduced that was in order to, first of all, it's really kind of natural way of a natural operation. But the motivation, I believe, was for rederiving Reingold's result, SL equals L, in a more kind of slightly cleaner and simpler way. So Reingold, based his breakthrough result on the zigzag product, maybe a couple of months or a year after the zigzag product was devised. And Rosenman and Vadan did the de-randomized scoring. I'm going to talk about it in a second, but I'm just going to say that in a prior work, again with Itai and Gal, but also Yuval Peled from the Hebrew University, we found, and that actually was before, we found the relevant equation for de-randomized scoring, which is this thing. Right, so with every combinatorial operations, we were able to find an analog or a corresponding kind of equations whose minimum at some interval tells you what omega is. Now, in the case for de-randomized squaring, we actually don't know its type. We have partial results saying that our lower bound is tight, but it's not sort of foolproof. It's tight in a slightly larger class of graphs. So it's an interesting open question to try to show its type. So let me just tell you what's the de-randomized squaring, because it's really a natural operation. It's maybe less known than the zigzag product. But in the space-bounded de-randomization field that I'm working on, actually de-randomized squaring proved to be really useful, more than the zigzag product. And you'll see why in a second, or maybe. So what's squaring? So if you forget about de-randomized, what's squaring? So if you have a graph G, then the square of G is just, it's the graph on the same vertex set, but the edges encode or correspond to length 2 walks in the original graph G. Right, so if you have 2 vertices in G, and there is a length 2 walk connecting them, 2 steps, 2 edges, then there's going to be an edge on the account of that walk between the 2 vertices. Another way of looking at, saying that differently, if you look at a specific vertex and its neighborhood, then if that's G, that's how the vertex see things at G, then because of it, all of its neighbors are going to be connected, because you can go from every vertex to every other vertex, every neighbor to every other neighbor through that vertex. Also, by the way, from a vertex to itself. So if you think about it, in G squared, what's going to happen is that the star that connects the neighbors of a vertex to it is going to be replaced with the complete graph with self-loops, excluding that vertex. That vertex kind of is left alone, maybe unless it has a self-loop or one of the neighbor has a self-loop or something like that, but that's what it is. So really, squaring is replacing stars with cliques. And squaring is great. When you square a graph, omega squares also, which is good because it's a number between 0 and 1. It makes it smaller. You want it to be smaller. But it's also bad because the graph becomes denser and denser if you keep doing that, right? For example, the degree of G was if it was D, if it was D regular, now the degree is going to be D squared, and usually if you do iterations and stuff like that, it's going to blow up. So the idea in randomized squaring is to do a sparse approximation of G squared. Oh, I think my battery is running low. 1 second, please. And here we have 1%. Good. So, so the idea is again to de-randomize the square, and more precisely, we are just going to do that by replacing, instead of having a clique like we did in the kind of actual square around every vertex, we are going to put a copy of H, where H is the small graph that we have, and note again that we need that the degree of G is going to be the number of vertices of H. So what's happening here is that we are kind of identifying every edge or leaving that vertex, or alternatively every neighbor of it. We identify it with a vertex of H, and then the edges of H are going to induce the edges between the neighbors of that vertex. And we're going to do that for every vertex, right? So it's going to be a union of those, maybe a weighted union. You count multiple edges with those edges. So now, for example, if the graph H has degree C, then the new graph is going to have degree C times D, rather than D squared in G squared, or C squared in the zigzag. So anyhow, it's lower degree. You don't square things, you just multiply them by something, which could be constant. Okay. So that's all I wanted to say about the de-randomized scoring. I do want to say one interesting corollary out of this work. I mean, the downside of this work, even though I don't quite see it as a downside, is that if you want to understand zigzagging with H, then you get a problem, you need to solve it, a minimization problem, you solve it, you solve the problem. But you can ask, can you understand something about zigzagging in general, not with a particular H? I mean, currently for every H you have a distinct problem you need to solve, and it's hard from the different numbers or from this function maybe to get information about zigzagging in general, but actually that's not the case. So you can do that. So what we prove is what we call a universal bound. We prove that for every vertex transitive graph as before, and for every G as before, again, it's going to be the regular, omega of the zigzag product is always bounded by this expression, 1 minus square root of C minus 1, minus little of 1, of course. And that has nothing to do with H, right? The bound is only depending on the fact that H is C-regular. So that's a universal bound in the sense that it holds for all C-regular graphs. Okay, no matter what their size is. Just you need G to have a degree which matches the size of H. And if you think about it, the degree of G zigzag H is C squared. So there is a kind of a quadratic dependence between the degree, not quadratic, quartic dependence between the degree and omega, right? The degree is C squared, and omega is roughly 1 over square root of C. And if this was to be a Ramanujan graph, it would have been like 1 over C, right? 1 over square root of the degree. So you can see here as a corollary that zigzags are quadratically far away from Ramanujan. So that may surprise you or may not surprise you. What is surprising, I think, is that is probably not the case for de-randomized scoring. So for de-randomized scoring, we don't have a conclusive proof, but our bounds and experiments definitely suggest that typically, and that's, I think, surprising myself, de-randomized scoring usually gives you something which approaches Ramanujan. So you de-randomize the square. You take the de-randomized scoring of G and H, you get a degree CD graph. What you see in experiments and the low bounds that we have in general suggest that omega is going to be 1 over the square root of CD. So it's going to be Ramanujan. So even though Zig-Zag and de Scuring are kind of siblings, they are very similar to each other in many senses. They actually behave very differently, which was surprising for us. Okay. Okay, so maybe let me just recap before concluding. So we talked about the fact that there are 3 branches of ways of arguing about graphs and constructing expanders in particular, either number or group theoretic, or combinatorial and linear algebraic, elementary linear algebraic ways, or analytic, using analytic machinery like free probability and also maybe now analytic combinatorics. And the goal of this, the point of these works, this sequence of works, which I hope people will continue, is to understand combinatorial operations using this analytic framework and machinery. Okay, so that's what I was talking about. Actually, in a prior work, even before the one about the randomized scoring, we considered another problem related to expanders. It's not even an operation on graphs per se, but rather a variant of random walks, which I'm going to talk about now briefly. And we use this analytic machinery to study that. So I just want to mention briefly what are rotating expanders. And I think it might be a good a way of saying a bit about why analytic is kind of what's the advantage of using analytic machinery, like why smooth is better. Okay. So again, so this last 2-3 minutes part, maybe 5 minutes part of the talk is going to be about rotating expanders, and this is joint work with Gal Maor. I think it appeared in stock 2023. So let me just remind you what are random walks first. So if you have a graph, I'm looking at this part now, and what's a random walk? You start at some vertex. Maybe it's random, maybe it's not random. Maybe there is a distribution, maybe it's fixed. But you start at some vertex, and then at every point in time, you choose a random neighbor, and you go to that neighbor. So maybe you got to this neighbor after one step, right? And then you continue from that. You choose another random neighbor you go to here, and maybe here, and so forth, until you end up somewhere. Now, random walks are extremely useful, and there is one caveat with random walks, at least on undirected graphs, which are the things we mostly use, especially in the context of expanders. Then the problem is that there is some parameter, it's actually omega of what's called the power graph, but let's not go into details. There is some parameter that deteriorates with the number of steps that you take. Here it's 6, right? It deteriorates exponentially with this number. And in different applications, that exponential deterioration is what kind of stops you from getting like really interesting results. Like in particular, maybe optimal small bias sets or very near optimal small bias sets. That was the motivation for this work. So what Gal and I tried to do is to find an alternative to random walks, which looks like a random walk. So it's kind of the same. So like with high probability, prior analysis will go through without any change. But this alternative won't have the downside of this parameter deteriorating exponentially. And indeed, we were able to come up with an alternative that deteriorates only linearly. We don't yet have applications for that, and I encourage you to find applications. I mean, it's not that there are no applications. There are going to be many applications of that if you can generalize what we did. Because we kind of studied the simplest case of kind of vanilla random walk. In applications, usually you have more things going on. I can't say more than that in a couple of minutes. So what's the idea? The idea is to say, well, I'm going to, so random walks are random walks. You start from a vertex, maybe it's random, maybe it's not, but then every step is going to be to a random neighbor. And in applications, what usually happens is that the adversary or whatever you're working against, he knows the graph and he knows where you're going, and he's going to use that despite the fact he doesn't know the randomness. So in applications also, the randomness is important. So you don't want to waste more random bits, even if it's not about pseudo randomness. The length of the random walk and the degree is going to be involved in the parameters. So you don't want to invest more randomness. So what we did was to prove that for every graph and for every walk length t, and anyhow, you can find permutations of the vertices of the graph. So this is some permutation of the Peterson graph, such that if you're going to do the usual random walk, but after each random step, you're going to use the permutations, which are deterministic permutations, then that exponential loss will become only linear. Okay, so what am I talking about here? So this is an example. So maybe you start from this vertex, and then you do the usual random step, right? You go here, but then instead of continuing the random step like in a vanilla random walk, we are going to use maybe the orange permutation that I showed earlier. I'm not sure it's actually consistent with what was there, but which will get you from here to here, right, to that vertex. And then you move from that vertex as usual. You take a random step, maybe you reach here, and then use the green permutation. There is a sequence of permutations that we find, or that we prove to exist, that may lead you to here. And then from here, you do another random step, and then maybe use the original permutation because you want to keep things undirected and so forth. So it turns out that this kind of rotating random walk has advantages, which I'm curious about whether they will find applications. But the point is that in terms of techniques, what analytic machinery gives you is a way of moving from the necessity to argue about what permutations are doing, which is usually difficult, to what rotations are doing, which is easier. Not easy, but easier. We have tools for that. So instead of talking about permutations, what's going to happen is, in a sense, we are going to take the adjacency matrix of the graph that we are starting with, and we are going to rotate its eigenvectors using a random unitary or rotation. So it's going to be real valued, but never mind. So that won't give you a graph. I mean, this was the adjacency matrix of some graph. This is it's the adjacency matrix of some graph, but then most likely you have with measure 1, you're going to have all possible edges with negative weights also. So it's not like you don't preserve the fact that if you start with a irregular graph, you end with a irregular graph. But nonetheless, I mean, it's definitely kind of easier to analyze, as you can imagine. It's smooth and nice, and finite free probability allows you to move from the necessity to argue about permutation to argue about rotations like that. It's not only rotations, it's also reflections, but never mind. Okay, so I hope that was somewhat informative. And that's it. So what I'm really curious about is to see if you can find other applications of free probability and finite free probability, or whatever we did, or and so forth. In general, analytic methods, I think should see more applications.